Good evening, fellow space enthusiasts. Tonight, let's embark on an exploration of captivating space facts. Imagine yourself venturing through the awe-inspiring depths of the universe, where ancient galaxies twirl in a cosmic dance of stars and nebulae. As we delve deeper, contemplate the serene mysteries of black holes, the graceful dance of gravitational waves, and the intricate interplay of dark matter and energy shaping the cosmos. Let these cosmic revelations ignite wonder and curiosity as we uncover the secrets of our vast universe. Thank you for joining us on this enlightening journey through space facts. May these cosmic insights spark your imagination and deepen your appreciation for the boundless wonders beyond. Good night, and may the brilliance of the stars illuminate your dreams. 1. The universe emerged approximately 13.8 billion years ago from an incredibly dense and hot state known as the Big Bang. This event marked the beginning of space, time, and the expansion of all matter and energy. Over billions of years, the universe evolved from a hot, uniform plasma into the diverse and structured cosmos we observe today, filled with galaxies, stars, planets, and cosmic phenomena. 2. The observable universe spans about 93 billion light-years in diameter. This vast expanse encompasses everything that can be observed from Earth, including billions of galaxies. Each galaxy is a collection of stars, gas, dust, and dark matter bound together by gravity. The scale of the observable universe provides a humbling perspective on the sheer size and complexity of cosmic structures. 3. Dark matter is a mysterious form of matter that makes up about 27% of the universe's total mass energy content. Unlike ordinary matter, which emits, absorbs, and reflects light, dark matter interacts primarily through gravitational forces. It plays a crucial role in the formation and evolution of galaxies, exerting gravitational influence that shapes their structure and dynamics. Despite its pervasive influence, dark matter has yet to be directly detected, posing one of the most significant mysteries in modern astrophysics. 4. Dark energy constitutes approximately 68% of the universe's energy density. It is a hypothetical form of energy that pervades all of space and is thought to be responsible for the accelerated expansion of the universe. Unlike dark matter, which acts as a gravitational attractor, dark energy behaves as a repulsive force, causing galaxies to move away from each other at an increasing rate over cosmic distances. The discovery of dark energy's existence in the late 1990s revolutionized our understanding of the universe's ultimate fate and continues to be a focus of intense scientific study. 5. There are over 100 billion galaxies in the observable universe. These galaxies vary widely in size, shape, and composition. They're classified into different types, including spiral galaxies like our Milky Way, which have a central bulge surrounded by spiral arms of stars, gas, and dust. Other galaxies include elliptical galaxies, which are more rounded and lack distinct spiral structure, and irregular galaxies, which exhibit chaotic shapes and often result from gravitational interactions with neighboring galaxies. 6. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape their gravitational pull. They form when massive stars collapse under their own gravity at the end of their life cycles, or through the merger of smaller black holes. Supermassive black holes, which can have masses millions to billions of times greater than that of the Sun, reside at the centers of most galaxies, including our own Milky Way. Despite their ominous reputation, black holes play a crucial role in the evolution of galaxies and the regulation of star formation. 7. The cosmic microwave background (CMB) is the residual radiation left over from the Big Bang. It fills the entire universe as a faint glow of microwave radiation, providing a snapshot of the universe when it was just 380,000 years old. Prior to this epoch, the universe was too hot and dense for light to travel freely. As the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing photons to travel unimpeded, creating the CMB. Studying the CMB provides astronomers with invaluable insights into the universe's early conditions, including its temperature fluctuations, composition, and overall geometry. 8. Exoplanets or extrasolar planets are planets that orbit stars beyond our solar system. Thousands of these planets have been discovered using methods like the transit method, which detects slight dimming of a star's light as a planet passes in front of it, and the radial velocity method, which measures the star's wobble due to gravitational pull from an orbiting planet. These exoplanets vary widely in size, composition, and distance from their host stars, ranging from gas giants similar to Jupiter to rocky, Earth-like planets. Some exoplanets are located in their star's habitable zone, where conditions might allow for liquid water and potentially life, sparking significant interest and ongoing research in the search for extraterrestrial life. 9. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as colliding black holes or neutron stars. Predicted by Albert Einstein's general theory of relativity in 1915, these waves were first directly detected by the Laser Interferometer Gravitational Wave Observatory LIGO in 2015. The discovery of gravitational waves opened a new window for observing and understanding the universe, allowing scientists to study cosmic events that are otherwise invisible, such as black hole mergers. Gravitational waves provide unique insights into the fundamental nature of gravity and the dynamics of extreme astrophysical phenomena. 10. The concept of a multiverse suggests that our universe might be one of many universes that coexist within a larger multiverse. This idea arises from various theories in cosmology and quantum physics, such as the inflationary multiverse, where different regions of space could inflate at different rates, creating separate bubble universes with distinct physical laws and constants. While the multiverse hypothesis remains speculative and unproven, it offers intriguing possibilities for explaining the fine-tuning of our universe's parameters that allow for the existence of galaxies, stars, and life. Research into the multiverse continues to challenge and expand our understanding of the cosmos. 11. The ultimate fate of the universe depends on its density, dark energy content, and the rate of its expansion. Several scenarios are possible, including the Big Freeze, where the universe continues to expand and cool until galaxies, stars, and eventually atoms become isolated in a dark, cold void. Another possibility is the Big Crunch, where the universe's expansion reverses, causing it to collapse back into a hot, dense state. A third scenario is the Big Rip, where dark energy causes the expansion to accelerate so rapidly that it tears apart galaxies, stars, planets, and even atomic particles. Current observations suggest that the universe is likely headed towards a Big Freeze, but the true fate remains an open question in cosmology. 12. Neutron stars are incredibly dense remnants of massive stars that have exploded in supernovae. Composed almost entirely of neutrons, these stars pack a mass greater than that of the Sun into a sphere with a diameter of just about 20 kilometers. Neutron stars have extremely strong magnetic fields and rapid rotation rates, with some spinning hundreds of times per second, known as pulsars. These stars provide valuable insights into the behavior of matter under extreme conditions, helping scientists study the fundamental properties of nuclear physics and the nature of matter at its densest state. Some neutron stars are also found in binary systems, where they can merge with other neutron stars or black holes, producing gravitational waves and heavy elements like gold and platinum. 13. Quasars are incredibly bright and distant objects powered by supermassive black holes at the centers of young galaxies. As matter falls into these black holes, it heats up and emits intense radiation, making quasars some of the brightest objects in the universe. Despite their immense distances from Earth, quasars are visible due to their high luminosity, often outshining their entire host galaxies. Studying quasars provides valuable information about the early universe, the growth of supermassive black holes, and the evolution of galaxies. 14. The Oort cloud is a hypothetical, distant region of the solar system, thought to be a spherical shell of icy bodies surrounding the Sun at a distance of up to 100,000 astronomical units (O). This region is believed to be the source of long-period comets, which have orbits that take them far beyond the outer planets and back toward the Sun over thousands of years. Although the Oort cloud has not been directly observed, its existence is inferred from the behavior and trajectories of comets. Understanding the Oort cloud helps scientists learn about the formation and evolution of the solar system. 15. The Kuiper Belt is a region of the solar system beyond the orbit of Neptune, extending from about 30 to 55 astronomical units from the Sun. It is populated by small icy bodies, dwarf planets like Pluto, and numerous comets. The Kuiper Belt is similar to the asteroid belt but is much larger and more massive. Studying objects in the Kuiper Belt provides insights into the early solar system and the processes that led to the formation of planets and other celestial bodies. The New Horizons mission, which flew by Pluto in 2015, has significantly increased our understanding of this distant region. 16. The Andromeda Galaxy, also known as M31, is the nearest spiral galaxy to the Milky Way and is located about 2.5 million light-years away. Andromeda is on a collision course with the Milky Way, with the two galaxies expected to merge in about 4.5 billion years. This future galactic collision will likely result in the formation of a single, larger elliptical galaxy. Observing Andromeda helps astronomers understand galaxy formation and evolution, as well as the dynamics of galactic interactions and mergers. The study of Andromeda also provides a glimpse into the future of our own galaxy's evolution. 17. Pulsars are a type of neutron star that emits beams of electromagnetic radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space and, if aligned with Earth, can be detected as regular pulses of radio waves, X-rays, or gamma rays. Pulsars are incredibly precise cosmic clocks with rotation periods ranging from milliseconds to a few seconds. Their consistent pulsing makes them valuable tools for studying extreme states of matter, testing theories of gravity, and even detecting gravitational waves. 18. The Hubble Space Telescope, launched in 1990, has revolutionized our understanding of the universe. Orbiting above Earth's atmosphere, Hubble has captured stunning images of distant galaxies, nebulae, and other cosmic phenomena with unprecedented clarity. Its observations have led to numerous discoveries, including the acceleration of the universe's expansion, the existence of dark energy, and the detailed study of planetary atmospheres and exoplanets. Hubble's legacy continues to inspire and advance astronomical research, with its successor, the James Webb Space Telescope, set to expand our observational capabilities even further. 19. The Great Red Spot on Jupiter is a massive storm that has been raging for at least 400 years, possibly much longer. This gigantic anticyclonic storm is about 1.3 times the diameter of Earth and is characterized by its reddish color and swirling clouds. The storm's longevity and persistence have puzzled scientists, as it is unlike any weather phenomenon on Earth. Studying the Great Red Spot and other atmospheric features of Jupiter helps scientists understand the dynamics of planetary atmospheres, including those of exoplanets. 20. The heliosphere is a vast bubble-like region of space dominated by the solar wind, a stream of charged particles emitted by the Sun. This bubble extends well beyond the orbit of Pluto, marking the boundary where the solar wind's influence wanes and interstellar space begins. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have both crossed the heliopause, the outer boundary of the heliosphere, entering interstellar space. These missions provide valuable data on the interaction between the solar wind and the interstellar medium, enhancing our understanding of the Sun's influence on the solar system and its protective role against cosmic radiation. 21. The concept of cosmic inflation suggests that the universe underwent a rapid exponential expansion during the first fraction of a second after the Big Bang. This theory helps explain the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. According to inflation theory, the universe expanded faster than the speed of light, smoothing out any initial irregularities and setting the stage for the formation of galaxies and other cosmic structures. Inflation remains a fundamental aspect of modern cosmology, providing insights into the conditions of the early universe. 22. The Crab Nebula is a supernova remnant located in the constellation Taurus, about 6,500 light-years from Earth. It was formed by a supernova explosion observed by Chinese and Arab astronomers in 1054 AD. At its center lies a rapidly rotating neutron star, or pulsar, which emits intense radiation and powers the nebula's luminosity. The Crab Nebula is one of the most studied objects in the sky, offering valuable information about the life cycle of stars, the mechanisms of supernova explosions, and the behavior of matter under extreme conditions. 23. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. Proposed by Dr. Frank Drake in 1961, the equation considers factors such as the rate of star formation, the fraction of stars with planetary systems, the number of planets that could support life, and the likelihood of intelligent life developing. While many of the variables remain uncertain, the Drake equation serves as a framework for discussions about the potential for extraterrestrial life and has inspired numerous searches for signals from other civilizations. 24. The Fermi paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations existing in the galaxy and the lack of evidence for or contact with such civilizations. Named after physicist Enrico Fermi, the paradox raises questions about the reasons for this silence, suggesting various explanations ranging from the rarity of intelligent life, the vast distances between stars, self-destruction of advanced civilizations, or the possibility that advanced beings are not using communication methods we can detect. The Fermi paradox continues to provoke debate and research into the search for extraterrestrial intelligence. SETI. 25. The Solar System is located within the Milky Way galaxy, which is a barred spiral galaxy containing over 100 billion stars. The Milky Way spans about 100,000 light-years in diameter and has a central bulge surrounded by a disk of stars, gas, and dust with spiral arms extending outward. Our solar system resides in one of these spiral arms, known as the Orion Arm, about 27,000 light-years from the galactic center. The study of the Milky Way helps astronomers understand the structure, dynamics, and evolution of spiral galaxies. 26. The electromagnetic spectrum encompasses all types of electromagnetic radiation, ranging from gamma rays with the shortest wavelengths to radio waves with the longest wavelengths. Different types of radiation reveal unique aspects of the universe, from high-energy phenomena like black holes and supernovae observed in X-rays and gamma rays to cooler objects like stars and planets observed in visible and infrared light. By using telescopes sensitive to various parts of the spectrum, astronomers can gather a comprehensive understanding of cosmic objects and processes. 27. The asteroid belt is a region of the solar system located between the orbits of Mars and Jupiter, containing millions of rocky bodies of various sizes. These asteroids are remnants from the early solar system that never coalesced into a planet due to the gravitational influence of Jupiter. The largest object in the asteroid belt is the dwarf planet Ceres, which has a diameter of about 940 kilometers. Studying asteroids provides insights into the composition and conditions of the early solar system, as well as the potential for asteroid mining and planetary defense. 28. The Hubble Deep Field is a series of images taken by the Hubble Space Telescope in the 1990s and 2000s, capturing an incredibly small and seemingly empty patch of sky. These images revealed thousands of galaxies, including some of the most distant and ancient galaxies ever observed, providing a glimpse into the early universe. The Hubble Deep Field observations demonstrated the vast number of galaxies in the universe and helped refine estimates of the total number of galaxies, contributing significantly to our understanding of cosmic evolution and the formation of galaxies. 29. The event horizon of a black hole is the boundary beyond which nothing can escape its gravitational pull, not even light. This boundary marks the point where the escape velocity exceeds the speed of light. Inside the event horizon, the gravitational forces are so strong that all paths lead inexorably toward the singularity, a point of infinite density where the laws of physics as we know them cease to apply. The study of event horizons and black holes offers deep insights into the nature of gravity, spacetime, and the fundamental limits of physical laws. 30. The Large Magellanic Cloud (LMC) and the Small Magellanic Cloud (SMC) are two irregular dwarf galaxies that are satellite galaxies of the Milky Way. Located approximately 160,000 and 200,000 light-years away, respectively, they are visible to the naked eye from the southern hemisphere. These galaxies are rich in gas and are sites of vigorous star formation. Studying the LMC and SMC helps astronomers understand galaxy interactions, star formation processes, and the dynamics of satellite galaxies in relation to their host galaxies. 31. The Voyager Golden Records are phonograph records that were launched aboard the Voyager 1 and Voyager 2 spacecraft in 1977. These records contain sounds and images intended to portray the diversity of life and culture on Earth, including music, greetings in 55 different languages, and various natural sounds. The Golden Records are a time capsule meant for any intelligent extraterrestrial life that might find the spacecraft. As of now, Voyager 1 and 2 are the farthest human-made objects from Earth, traveling through interstellar space and carrying these messages from humanity. 32. Saturn's rings are one of the most spectacular features in the solar system. Composed primarily of ice particles with some rocky debris and dust, these rings extend up to 175,000 miles to 182,000 kilometers from the planet but are surprisingly thin, typically only about 30 feet 10 meters thick. The rings are divided into several sections labeled alphabetically in the order they were discovered. Studying Saturn's rings provides insights into the processes of planetary ring formation and dynamics, as well as the history and evolution of the solar system. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided detailed images and data about the rings, revealing their intricate structure and composition. 33. The Kuiper Belt is a region of the solar system extending from the orbit of Neptune at about 30 astronomical units (AU) from the Sun to approximately 55 astronomical units. It is home to many small, icy bodies and dwarf planets, including Pluto, Haumea, and Makemake. The Kuiper Belt is similar to the asteroid belt but far larger and more massive. It is believed to be a remnant of the early solar system, containing primordial objects that can provide insights into its formation and evolution. The study of the Kuiper Belt is crucial for understanding the distribution and composition of the solar system's outer regions. 34. Gamma ray bursts (GRBS) are the most energetic events in the universe, releasing as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. They are thought to result from the collapse of massive stars or the merger of neutron stars. GRBS are detected by their brief flashes of gamma rays, followed by an afterglow at various wavelengths. These bursts provide valuable information about the deaths of massive stars, the formation of black holes, and the behavior of matter under extreme conditions. The study of GRBS also helps astronomers understand the rate of star formation in the early universe. 35. The Fermi paradox, named after physicist Enrico Fermi, addresses the apparent contradiction between the high probability of extraterrestrial civilizations existing in the Milky Way galaxy and the lack of evidence or contact with such civilizations. Despite the vast number of stars and potentially habitable planets, we have not observed any definitive signs of intelligent life. Several hypotheses attempt to explain this paradox, including the possibility that advanced civilizations are rare, the immense distances between stars, the likelihood of self-destruction of intelligent life, or the possibility that extraterrestrial beings are avoiding contact. The Fermi paradox continues to inspire scientific inquiry and debate about the search for extraterrestrial intelligence SETI 36. The James Webb Space Telescope JWST is a highly anticipated space observatory set to be the successor to the Hubble Space Telescope. Scheduled for launch in December 2021, JWST is designed to observe the universe in the infrared spectrum, allowing it to see through dust clouds and study the formation of stars and planets, the evolution of galaxies, and the atmospheres of exoplanets. Its advanced capabilities will enable astronomers to look further back in time than ever before, to just a few 100 million years after the Big Bang. JWST's mission promises to revolutionize our understanding of the cosmos and address some of the most fundamental questions in astronomy and astrophysics. 37. The International Space Station ISS is a habitable artificial satellite that orbits Earth at an average altitude of approximately 420 kilometers to 160 miles. It is a joint project involving space agencies from the United States NASA, Russia Roscosmos, Europe ESA, Japan JAXA, and Canada CSA. The ISS serves as a microgravity and space environment research laboratory where scientific research is conducted in astrobiology, astronomy, meteorology, physics, and other fields. It has been continuously occupied since November 2000, providing valuable data on the effects of long-term space flight on the human body, which is crucial for future deep space missions. 38. Titan, Saturn's largest moon, is one of the most intriguing bodies in the solar system. It is the only moon known to have a dense atmosphere, composed mostly of nitrogen with traces of methane and hydrogen. Titan's surface features lakes, rivers, and seas of liquid methane and ethane, as well as vast dunes of organic material. The Cassini-Huygens mission, which included the Huygens probe landing on Titan's surface in 2005, revealed the moon's complex geology and potential for prebiotic chemistry. Titan's unique environment makes it a prime candidate for studying the conditions that might lead to the development of life. 39. The Great Attractor is a gravitational anomaly located in the direction of the constellation Centaurus, about 150 to 250 million light-years from the Milky Way. It is drawing galaxies, including our own, towards it with a gravitational force equivalent to a concentration of tens of thousands of Milky Way-sized galaxies. Despite its immense gravitational pull, the exact nature of the Great Attractor remains a mystery because it lies behind the zone of avoidance, a region obscured by the Milky Way's plane. Understanding the Great Attractor helps astronomers learn more about the large-scale structure of the universe and the distribution of mass. 40. The Hertzsprung-Russell HR diagram is a fundamental tool in astronomy that plots stars according to their luminosity intrinsic brightness and their surface temperature or color. This diagram reveals distinct groupings and relationships among different types of stars, such as the main sequence, red giants, white dwarfs, and supergiants. The HR diagram helps astronomers understand stellar evolution as stars move through different regions of the diagram over their lifetimes. By studying the positions of stars on the HR diagram, astronomers can infer their age, composition, and future development, providing key insights into the life cycles of stars and the dynamics of galaxies. 41. Dark matter is a mysterious substance that makes up about 27% of the universe's mass-energy content, while ordinary matter, which makes up stars, planets, and all visible structures, comprises only about 5%. Dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The exact nature of dark matter remains one of the biggest mysteries in cosmology. Scientists propose that it could be composed of hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, but it has yet to be directly detected. 42. The cosmic microwave background (CMB) is the afterglow of the Big Bang, a faint radiation that fills the universe and can be observed in all directions. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB provides a snapshot of the universe approximately 380,000 years after the Big Bang, when it had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely. The CMB's uniformity and slight fluctuations offer crucial information about the early universe's conditions, the formation of large-scale structures, and the overall geometry and composition of the cosmos. 43. The Sun, a G-type main sequence star or G-dwarf, is the central and most massive object in our solar system, accounting for about 99.86% of its total mass. It is approximately 4.6 billion years old and is expected to remain in its main sequence phase, where it fuses hydrogen into helium, for another 5 billion years. The Sun's energy, produced through nuclear fusion in its core, powers the climate and weather systems on Earth, making life possible. Understanding the Sun's behavior, including solar flares and sunspots, helps scientists predict space weather and its impact on Earth's technological systems. 44. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are formed from the remnants of massive stars that have undergone gravitational collapse at the end of their life cycles. There are different types of black holes, stellar mass black holes, which form from the collapse of individual stars. Supermassive black holes, found at the centers of galaxies and millions to billions of times more massive than the Sun. And intermediate mass black holes, which are less common and may form through the merging of smaller black holes. The study of black holes helps scientists understand extreme gravitational effects and the fundamental nature of space and time. 45. Exoplanets or extrasolar planets are planets that orbit stars outside our solar system. The first confirmed detection of an exoplanet was in 1992, and since then, thousands of exoplanets have been discovered with varying sizes, compositions, and orbital characteristics. Some exoplanets are Earth-like and reside in the habitable zone of their parent stars, where conditions might be right for liquid water and potentially life. The study of exoplanets helps scientists understand planetary formation and the potential for life beyond Earth, with missions like Kepler and TESS contributing significantly to this field of research. 46. The Andromeda Milky Way collision is a future event in which the Andromeda Galaxy and the Milky Way are expected to collide and merge. This galactic collision is predicted to occur in about 4.5 billion years. Despite the vast number of stars in each galaxy, the immense distances between them mean that actual stellar collisions are unlikely. Instead, the gravitational forces will reshape both galaxies, likely forming a new elliptical galaxy. This event will provide a spectacular view of galactic evolution and offers insights into how such mergers influence the formation and dynamics of galaxies. 47. Neutrinos are extremely lightweight and weakly interacting subatomic particles produced by nuclear reactions in stars during supernovae and in other cosmic events. Despite their abundance, neutrinos are challenging to detect because they rarely interact with matter. Billions of neutrinos pass through every square centimeter of Earth every second. Neutrino observatories, such as the IceCube Neutrino Observatory in Antarctica, are designed to detect these elusive particles. Studying neutrinos helps scientists understand fundamental particle physics, the processes occurring in the Sun and other stars, and high-energy cosmic phenomena. 48. The heliosphere is a vast bubble-like region of space dominated by the solar wind, a stream of charged particles released by the Sun. It extends well beyond the orbit of Pluto, marking the boundary where the solar wind's influence wanes and interstellar space begins. The outer edge of the heliosphere is known as the heliopause. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have both crossed the heliopause, entering interstellar space. Studying the heliosphere provides valuable information about the interaction between the solar wind and the interstellar medium, the protective role of the Sun against cosmic radiation, and the dynamics of our solar system's boundary. 49. The Large Hadron Collider (LHC) is the world's largest and most powerful particle accelerator, located near Geneva, Switzerland. Operated by CERN, the European Organization for Nuclear Research, the LHC consists of a 27-kilometer ring of superconducting magnets and advanced accelerating structures. It accelerates protons and heavy ions to nearly the speed of light, causing them to collide with unprecedented energy levels. These collisions allow scientists to study fundamental particles and forces, leading to groundbreaking discoveries like the Higgs boson in 2012. The LHC's experiments provide insights into the fundamental building blocks of the universe and the laws governing their interactions. 50. The Kuiper Belt and the scattered disk are two distinct regions of the solar system beyond Neptune, containing many small icy bodies and dwarf planets. The Kuiper Belt, extending from about 30 to 55 astronomical units from the Sun, is a relatively flat, disk-shaped region home to objects like Pluto, Haumea, and Makemake. The scattered disk overlaps with the Kuiper Belt but extends much further out and is characterized by more eccentric and inclined orbits. These regions are remnants of the early solar system, and studying them helps scientists understand planetary formation, the migration of giant planets, and the distribution of small bodies in the outer solar system. 51. The James Webb Space Telescope JWST, launched in December 2021, is the most powerful space telescope ever built. It observes the universe in infrared light, allowing it to see through dust clouds and study the formation of stars and planets, the evolution of galaxies, and the atmospheres of exoplanets. JWST's advanced technology enables it to look further back in time than ever before, to just a few 100 million years after the Big Bang. This groundbreaking telescope promises to revolutionize our understanding of the cosmos, addressing some of the most fundamental questions in astronomy and astrophysics. 52. The South Polar Basin is one of the largest and oldest impact craters on the Moon, located on the lunar far side. It spans about 2,500 kilometers in diameter and is roughly 13 kilometers deep. This massive basin was formed by a colossal impact event early in the Moon's history, providing a window into the Moon's internal structure and geological evolution. Studying the South Polar Basin helps scientists understand the history of lunar impacts, the processes that shaped the Moon's surface, and the potential for future lunar exploration and resource utilization. 53. The Oort cloud is a theoretical, distant region of the solar system, extending from about 2,000 to 100,000 astronomical unit from the Sun. It is believed to be a vast, spherical shell of icy bodies and comets, remnants from the formation of the solar system. The Oort cloud is thought to be the source of long-period comets, which take more than 200 years to complete an orbit around the Sun. While no direct observations of the Oort cloud have been made, its existence is inferred from the trajectories of these comets. Studying the Oort cloud helps scientists understand the solar system's boundaries and the early processes that shaped it. 54. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. Predicted by Albert Einstein's general theory of relativity in 1916, gravitational waves were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO. These waves carry information about their origins and the nature of gravity, providing a new way to observe the universe. The detection of gravitational waves has opened a new era in astrophysics, allowing scientists to study cosmic events that were previously invisible through traditional electromagnetic observations. 55. The cosmic web is the large-scale structure of the universe, composed of vast filaments of galaxies and dark matter, separated by enormous voids. These filaments form a complex, web-like network with galaxy clusters located at the intersections. The cosmic web is a result of the gravitational collapse of matter over billions of years, following the initial density fluctuations in the early universe. Observing and mapping the cosmic web helps astronomers understand the distribution of matter in the universe, the formation and evolution of galaxies, and the influence of dark matter and dark energy on cosmic structures. 56. A magnetar is a type of neutron star with an extremely strong magnetic field, about 1,000 times more powerful than that of a typical neutron star. These intense magnetic fields can cause starquakes on the magnetar's surface, releasing vast amounts of energy in the form of X-rays and gamma rays. Magnetars are relatively rare, with only about 30 known in the Milky Way. Their study provides insights into the behavior of matter under extreme magnetic fields, the life cycles of massive stars, and the mechanisms behind high-energy astrophysical phenomena. Magnetars also offer opportunities to test fundamental physics in extreme conditions. 57. The Hubble Space Telescope, launched in 1990, has revolutionized our understanding of the universe. Orbiting above Earth's atmosphere, it provides unprecedented clarity in observing distant galaxies, nebulae, and other celestial objects. The Hubble has contributed to numerous groundbreaking discoveries, such as the accelerating expansion of the universe, the existence of supermassive black holes in galaxy centers, and detailed views of planets in our solar system. Its deep field images have revealed thousands of previously unseen galaxies, offering a glimpse into the universe's early stages and helping refine estimates of its age and size. 58. The Alpha Centauri system is the closest star system to our solar system, located about 4.37 light-years away. It consists of 3 stars, Alpha Centauri and B, which form a binary pair, and Proxima Centauri, a red dwarf that is slightly closer to Earth. Proxima Centauri has at least 2 known exoplanets, including Proxima b, which orbits within the star's habitable zone where liquid water might exist. The proximity of the Alpha Centauri system makes it a prime target for future interstellar exploration and the search for extraterrestrial life. 59. Solar wind is a stream of charged particles, primarily electrons and protons, emitted by the Sun's outer atmosphere, or corona. This continuous flow of particles spreads throughout the solar system, influencing planetary atmospheres and creating phenomena such as the aurora's northern and southern lights on Earth. The solar wind interacts with Earth's magnetosphere, protecting us from harmful solar radiation but also posing risks to satellites and space missions. Studying the solar wind helps scientists understand the sun's activity, space weather, and its effects on technological systems and astronaut safety. 60. The cosmic microwave background (CMB) is the remnant radiation from the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. This faint glow permeates the entire sky and is nearly uniform in all directions, with tiny temperature fluctuations that reveal information about the early universe's density and composition. The CMB's discovery in 1965 provided strong evidence for the Big Bang theory. Detailed measurements of the CMB by missions such as COBE, WMAP, and Planck have helped refine our understanding of the universe's age, composition, and evolution, including the conformation of dark matter and dark energy. 61. Quasars are extremely luminous active galactic nuclei powered by supermassive black holes at the centers of distant galaxies. They emit immense amounts of energy across the electromagnetic spectrum, often outshining their host galaxies. The energy comes from the accretion disk of gas and dust spiraling into the black hole, where friction and gravitational forces heat the material to incredibly high temperatures. Quasars can be observed billions of light years away, making them valuable probes of the early universe and galaxy formation. Studying quasars helps scientists understand the growth of supermassive black holes and the evolution of galaxies over cosmic time. 62. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, and if aligned with Earth, they appear as periodic pulses of radiation, hence the name pulsar. Pulsars are incredibly precise cosmic clocks, with some rotating hundreds of times per second. They are used by astronomers to study extreme states of matter, test theories of gravity, and even detect gravitational waves through timing variations in pulsar signals caused by passing waves. The discovery of pulsars has deepened our understanding of the life cycles of massive stars and the behavior of matter under extreme conditions. 63. The Kuiper Belt is a region of the solar system beyond Neptune, populated by small, icy bodies and dwarf planets, including Pluto, Haumea, and Makemake. Extending from about 30 to 55 astronomical units from the Sun, the Kuiper Belt is thought to be a remnant from the early solar system, containing primordial material that never coalesced into a planet. Studying Kuiper Belt objects provides insights into the formation and evolution of the solar system, the distribution of different types of bodies, and the processes that shaped the outer solar system. The New Horizons mission, which flew by Pluto in 2015, has provided detailed observations of this distant region. 64. The Great Red Spot on Jupiter is a massive, persistent anticyclonic storm located in the planet's southern hemisphere. It has been continuously observed for over 350 years, making it one of the longest-lasting storms in the solar system. The Great Red Spot measures about 16,350 kilometers, 10,159 miles in diameter, large enough to fit Earth inside it. The storm's reddish color is thought to be due to the complex organic molecules or phosphorus compounds in the upper atmosphere, though its exact composition remains a mystery. Studying the Great Red Spot helps scientists understand Jupiter's atmospheric dynamics, weather patterns, and the behavior of giant planet atmospheres in general. 65. The Drake equation, formulated by astrophysicist Frank Drake in 1961, is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the rate of star formation, the fraction of stars with planetary systems, the number of planets that could potentially support life, and the likelihood of life developing into intelligent beings capable of communication. Although many of the parameters are still uncertain, the Drake equation has been instrumental in guiding the search for extraterrestrial intelligence SETI and framing discussions about the existence of life beyond Earth. 66. The Event Horizon Telescope (EHT) is a global network of radio telescopes that works together to create an Earth-sized virtual telescope capable of imaging the event horizon of black holes. In 2019, the EHT collaboration released the first-ever image of a black hole's event horizon located in the center of the galaxy M87. This historic achievement provided direct visual evidence of black holes and confirmed predictions of Einstein's general theory of relativity. The EHT continues to study the environments around supermassive black holes, offering insights into their properties, accretion processes, and the nature of gravity in extreme conditions. 67. Enceladus, one of Saturn's moons, is a prime candidate for the search for extraterrestrial life within our solar system. This small, icy moon has a subsurface ocean beneath its icy crust, which is believed to be in contact with a rocky core, potentially providing the necessary conditions for life. The Cassini spacecraft discovered geysers erupting from Enceladus's south polar region, ejecting water vapor, ice particles, and organic compounds into space. These findings suggest that hydrothermal activity occurs on the ocean floor, creating a potentially habitable environment. The study of Enceladus helps scientists understand the potential for life in icy worlds and informs future missions to explore its subsurface ocean. 68. The multiverse theory proposes that our universe is just one of many universes that exist. These multiple universes, collectively known as the multiverse, could have different physical laws, constants, and conditions. The idea arises from various theories in physics, including string theory, cosmic inflation, and quantum mechanics. While the multiverse theory remains speculative and lacks direct observational evidence, it provides a possible explanation for the fine-tuning of the fundamental constants in our universe and offers intriguing possibilities for the nature of reality. The study of the multiverse challenges our understanding of space, time, and the fundamental nature of existence. 69. The Fermi paradox addresses the apparent contradiction between the high probability of extraterrestrial civilizations in our galaxy and the lack of evidence or contact with such civilizations. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox has led to various hypotheses to explain this discrepancy. These include the possibility that intelligent civilizations are rare, that they self-destruct before becoming capable of interstellar communication, or that they deliberately avoid contact with us. The Fermi paradox continues to be a central question in the search for extraterrestrial intelligence SETI and the study of life's potential in the universe. 70. The Chicxulub crater, located on the Yucatan Peninsula in Mexico, is the impact site of a massive asteroid or comet that struck Earth about 66 million years ago. This event is widely believed to have caused the mass extinction that wiped out the dinosaurs and many other species at the end of the Cretaceous period. The impact released energy equivalent to billions of atomic bombs, triggering tsunamis, wildfires, and a nuclear winter effect that drastically altered Earth's climate. Studying the Chicxulub crater helps scientists understand the role of impact events in shaping Earth's history and the potential threats posed by near-Earth objects. 71. The Kuiper Belt is a region of the solar system beyond Neptune, populated by small, icy bodies and dwarf planets, including Pluto, Haumea, and Makemake. Extending from about 30 to 55 astronomical unit from the Sun, the Kuiper Belt is thought to be a remnant from the early solar system, containing primordial material that never coalesced into a planet. Studying Kuiper Belt objects provides insights into the formation and evolution of the solar system, the distribution of different types of bodies, and the processes that shaped the outer solar system. The New Horizons mission, which flew by Pluto in 2015, has provided detailed observations of this distant region. 72. The heliosphere is a vast bubble-like region of space dominated by the solar wind, a stream of charged particles released by the Sun. It extends well beyond the orbit of Pluto, marking the boundary where the solar wind's influence wanes and interstellar space begins. The outer edge of the heliosphere is known as the heliopause. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have both crossed the heliopause, entering interstellar space. Studying the heliosphere provides valuable information about the interaction between the solar wind and the interstellar medium, the protective role of the Sun against cosmic radiation, and the dynamics of our solar system's boundary. 73. Gamma-ray bursts. Gamma-ray bursts, GRBS, are the brightest electromagnetic events known in the universe, emitting powerful bursts of gamma-ray radiation. They are thought to result from cataclysmic events such as the collapse of massive stars or the merging of neutron stars. GRBS can last from milliseconds to several minutes and are detected across vast distances in the universe. Studying GRBS helps astronomers understand the most energetic events in the cosmos, the formation of black holes and neutron stars, and the evolution of galaxies. 74. Tidal forces. Tidal forces occur due to the gravitational interaction between celestial bodies, causing deformations or disruptions. For example, tidal forces from the moon cause ocean tides on Earth. Similarly, extreme tidal forces can stretch and tear apart objects like comets and asteroids passing close to massive planets or stars. Tidal forces also play a role in shaping the orbits of moons around planets and potentially influencing the internal structures of celestial bodies. 75. The interstellar medium. The interstellar medium ISM is the matter and radiation that exists in the space between star systems within a galaxy. It consists mainly of gas, predominantly hydrogen and helium, and dust grains. The ISM plays a crucial role in the formation and evolution of stars and planetary systems. It serves as the reservoir of raw material from which stars and planetary systems form, and it influences their evolution through processes such as star formation, supernova explosions, and the recycling of material between generations of stars. 76. Cosmic inflation. Cosmic inflation is a theoretical period of rapid expansion that occurred in the fraction of a second after the Big Bang. This inflationary phase is thought to explain the uniformity and flatness of the universe on large scales, as well as the origin of the small density fluctuations that eventually gave rise to the formation of galaxies and cosmic structures. While direct evidence of cosmic inflation remains elusive, its predictions have been supported by observations such as the cosmic microwave background radiation and the large-scale distribution of galaxies. 77. White dwarfs are dense remnants of stars that have exhausted their nuclear fuel and shed their outer layers. They typically have masses similar to that of the Sun but are compressed into a size comparable to Earth. White dwarfs are extremely hot when formed, gradually cooling over billions of years. They represent the final stage of evolution for most stars, including our Sun, after they have gone through red giant and planetary nebula phases. Study white dwarfs provides insights into stellar evolution, the fate of our Sun, and the potential formation of supernovae and planetary nebulae. 78. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from various sources, including supernovae explosions, active galactic nuclei, and other high-energy events. Cosmic rays constantly bombard Earth's atmosphere, where they produce secondary particles and ionize atoms, contributing to atmospheric chemistry and radiation levels. Understanding cosmic rays helps scientists investigate astrophysical processes, the structure of galaxies, and their effects on planetary atmospheres and biological organisms. 79. The Roche limit is the distance within which a celestial body, held together by its own gravity, will disintegrate due to tidal forces exerted by a larger body. It plays a critical role in understanding satellite systems, such as rings around planets and the breakup of small moons or asteroids. The Roche limit depends on the densities and sizes of the two bodies involved, as well as their relative speeds and orbital parameters. Observations of objects near their Roche limits provide insights into gravitational interactions, orbital dynamics, and the formation of planetary rings. 80. The cosmic microwave background (CMB) is the thermal radiation left over from the Big Bang, filling the universe and observable in all directions. It represents the earliest light emitted in the universe's history, about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. The CMB appears nearly uniform in temperature but contains subtle temperature fluctuations that provide crucial information about the universe's composition, age, and early conditions. Detailed measurements of the CMB by spacecraft like COBE, WMAP, and Planck have confirmed key predictions of the Big Bang theory and refined our understanding of cosmic evolution. 81. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. It is estimated to make up about 27% of the universe's total mass energy content, significantly outweighing ordinary matter such as stars, planets, and galaxies. Dark matter plays a crucial role in the formation and evolution of large-scale structures in the universe, such as galaxies and galaxy clusters. Understanding its nature remains one of the biggest puzzles in modern astrophysics and cosmology. 82. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. They are composed almost entirely of neutrons packed together in a solid state with a density comparable to atomic nuclei. Neutron stars are typically about the size of a city, approximately 20 kilometers in diameter, but can have masses greater than that of the Sun. Their strong gravitational fields and rapid rotation rates make them natural laboratories for studying extreme physics, including nuclear matter, strong magnetic fields, and relativistic effects. 83. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It factors in variables such as the rate of star formation, the fraction of stars with planetary systems, and the probability of life developing on suitable planets. Although the values of these parameters are uncertain, the Drake equation provides a framework for discussing the likelihood of intelligent life elsewhere in the universe and guides the search for extraterrestrial intelligence. SETI 84. The asteroid belt is a region of the solar system located between the orbits of Mars and Jupiter, populated by millions of small rocky bodies known as asteroids. These asteroids vary in size from tiny fragments to large bodies several hundred kilometers in diameter. Contrary to popular perception, the asteroid belt is mostly empty space, with asteroids widely separated by distances much greater than their sizes. Studying asteroids provides insights into the early solar system's formation and the potential threats posed by near-Earth objects. 85. Supernovae are powerful stellar explosions that occur at the end of a massive star's life. They can briefly outshine entire galaxies and release immense amounts of energy and elements into space. Supernovae are classified into several types, including Type A caused by the collapse of a white dwarf in a binary system, and Type 2 resulting from the core collapse of massive stars. These cosmic events play a crucial role in enriching the interstellar medium with heavy elements necessary for planet formation and life. 86. Hubble's law describes the relationship between the distance of galaxies from Earth and their recessional velocity speed at which they are moving away. It is expressed as v equals h eb d, where v is the recessional velocity, d is the distance, and h is the Hubble constant, a measure of the rate of expansion of the universe. Hubble's law provides evidence for the expansion of the universe and has been instrumental in determining the age and size of the cosmos. 87. The Oort cloud is a hypothetical region surrounding the solar system, extending from about 2,000 to 200,000 astronomical units from the Sun. It is believed to be a reservoir of icy planetesimals, including comets, that originated from the early solar system's formation. The Oort cloud is thought to contain billions of objects, with orbits influenced by passing stars and galactic tides. Comets originating from the Oort cloud occasionally enter the inner solar system, becoming visible as they approach the Sun. 88. The habitable zone, or Goldilocks zone, is the region around a star where conditions are favorable for liquid water to exist on a planet's surface. This zone is determined by the star's luminosity and the planet's distance from it, ensuring temperatures are neither too hot nor too cold for water to remain in a liquid state. Identifying planets within their star's habitable zone is crucial in the search for extraterrestrial life and understanding the potential habitability of exoplanetary systems. 89. Quasars are extremely luminous and distant objects powered by supermassive black holes at the centers of galaxies. They emit vast amounts of energy across the electromagnetic spectrum and are some of the brightest sources in the universe. Quasars provide insights into the early universe's conditions and the growth of galaxies. 90. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects such as merging black holes or neutron stars. Predicted by Einstein's theory of general relativity, gravitational waves were first directly detected in 2015 by the LIGO and Virgo collaborations. Studying gravitational waves allows astronomers to explore phenomena inaccessible through traditional electromagnetic observations. 91. The cosmic microwave background (CMB) is the afterglow of the Big Bang, filling the universe uniformly with microwave radiation. Discovered in 1965, the CMB provides a snapshot of the universe about 380,000 years after the Big Bang, revealing its early structure and composition. Detailed measurements of the CMB have confirmed many predictions of the Big Bang theory. 92. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape from them. They form from the remnants of massive stars that have collapsed under their own gravity. Studying black holes helps scientists understand the nature of spacetime, the physics of extreme gravity, and the evolution of galaxies and the universe. 93. Redshift is a phenomenon where light from distant galaxies and celestial objects appears shifted towards longer wavelengths due to the expansion of the universe. It is a crucial indicator of cosmic distances and helps astronomers measure the expansion rate of the universe. Redshift provides evidence for the Big Bang theory and informs our understanding of the universe's large-scale structure. 94. The Kuiper Belt is a region of the solar system beyond Neptune, populated by icy bodies and dwarf planets such as Pluto, Haumea, and Makemake. It is believed to be a relic of the early solar system's formation, containing remnants that never coalesced into larger planets. The New Horizons mission provided detailed observations of Pluto and its moons, offering insights into the Kuiper Belt's composition and dynamics. 95. The heliosphere is a vast bubble-like region of space dominated by the solar wind, a stream of charged particles released by the Sun. It extends well beyond the orbit of Pluto and marks the boundary where the solar wind's influence wanes and interstellar space begins. Voyager 1 and Voyager 2 have crossed the heliopause, entering interstellar space and providing valuable data on the outer reaches of our solar system. 96. The Great Red Spot is a massive, persistent anticyclonic storm on Jupiter located in its southern hemisphere. It has been observed for over 350 years and is larger than Earth itself. The Great Red Spot's reddish color is thought to be due to complex organic molecules or phosphorus compounds in Jupiter's atmosphere. Studying this storm helps scientists understand Jupiter's atmospheric dynamics and the behavior of giant planet atmospheres in our solar system. 97. The Hubble Space Telescope, launched in 1990, has revolutionized astronomy by observing celestial objects without the distortion of Earth's atmosphere. Located in low Earth orbit, Hubble has captured stunning images of distant galaxies, nebulae, and other cosmic phenomena. Its observations have led to significant discoveries about the universe's expansion rate, the age of galaxies, and the presence of supermassive black holes at the centers of galaxies. 98. Exoplanets are planets that orbit stars outside our solar system. They come in a wide range of sizes and compositions, from rocky worlds like Earth to gas giants like Jupiter and Neptune. The discovery of exoplanets has accelerated since the 1990s, with thousands now confirmed. Techniques such as the transit method, detecting dips in a star's brightness as a planet passes in front of it, and radial velocity method, detecting a star's wobble caused by an orbiting planet's gravitational pull, have been instrumental in these discoveries. 99. Dark energy is a mysterious form of energy thought to permeate all of space and accelerate the universe's expansion. It is inferred from observations of distant supernovae and the large-scale distribution of galaxies. Dark energy is believed to account for about 68% of the universe's total energy content, making it a dominant component of the universe's composition. Understanding dark energy is one of the key challenges in modern cosmology and may hold clues to the universe's ultimate fate. 100. Astrobiology is the interdisciplinary study of the origin, evolution, distribution, and future of life in the universe. It combines elements of biology, astronomy, chemistry, geology, and physics to investigate the conditions and processes that may support life beyond Earth. Astrobiologists explore extreme environments on Earth and search for habitable conditions on other planets, moons, and celestial bodies. The search for extraterrestrial life is a central focus of astrobiology, with missions to Mars and ocean worlds like Europa and Enceladus aiming to find evidence of past or present life. 101. The Fermi paradox is the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of evidence for or contact with such civilizations. Named after physicist Enrico Fermi, who first raised the question, the paradox considers factors such as the vastness of the universe, the potential for advanced technology, and the lack of observable evidence. Proposed solutions range from the possibility that intelligent civilizations are rare or short-lived to the idea that they may communicate or exist in ways beyond current human understanding. 102. The James Webb Space Telescope JWST is a large, space-based observatory set to launch in the near future. It is designed to be the successor to the Hubble Space Telescope and will observe the universe in infrared wavelengths. JWST's primary goals include studying the formation of galaxies, stars, and planetary systems, as well as investigating the potential habitability of exoplanets. Equipped with advanced technology, JWST promises to provide unprecedented insights into the early universe and cosmic evolution. 103. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity, where the gravitational field of a massive object like a galaxy or a cluster of galaxies bends and distorts light from objects behind it. This effect can magnify, distort, or create multiple images of the background object, allowing astronomers to study distant galaxies, black holes, and other cosmic phenomena that would otherwise be too faint or distant to observe directly. Gravitational lensing serves as a powerful tool for understanding the distribution of dark matter and the geometry of the universe. 104. Neutrinos are subatomic particles with very little mass and no electric charge. They are produced in various astrophysical processes, including nuclear reactions in stars, supernovae explosions, and high-energy cosmic events like gamma-ray bursts. Neutrinos are extremely difficult to detect because they interact very weakly with matter, passing through most substances without leaving a trace. Detecting neutrinos from astrophysical sources provides unique insights into these energetic events and can help verify theories about particle physics and the behavior of matter under extreme conditions. 105. Gamma-ray bursts (GRBS) are short-lived bursts of high-energy gamma-ray radiation originating from distant galaxies. They are among the most energetic events in the universe, lasting from milliseconds to several minutes. GRBS are thought to be produced by supernovae, the collision of neutron stars, or the formation of black holes. They provide valuable insights into the early universe's conditions, the physics of extreme cosmic explosions, and the formation of black holes. 106. The cosmic microwave background radiation, CMB, is the residual thermal radiation left over from the Big Bang, filling the universe uniformly in all directions. Discovered in 1965, it provides a snapshot of the universe about 380,000 years after the Big Bang, when atoms first formed. The CMB appears as a faint glow of microwave radiation, with tiny fluctuations revealing information about the universe's composition, age, and initial conditions. Detailed observations of the CMB by satellites like COBE, WMAP, and Planck have confirmed many predictions of the The Big Bang Theory. 107. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. They consist almost entirely of neutrons packed into a sphere only about 20 kilometers in diameter but with masses greater than that of the Sun. Some neutron stars, known as magnetars, possess extremely powerful magnetic fields, trillions of times stronger than Earth's magnetic field. These magnetars occasionally produce intense bursts of X-rays and gamma rays, providing insights into the extreme physics of matter and their intense gravitational and magnetic fields. 108. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It factors in variables such as the rate of star formation, the fraction of stars with planetary systems, and the probability of life developing on suitable planets. Although the values of these parameters are uncertain, the Drake equation provides a framework for discussing the likelihood of intelligent life elsewhere in the universe and guides the search for extraterrestrial intelligence. SETI. 109. Interstellar travel refers to human or robotic missions traveling between stars within a galaxy. Achieving interstellar travel presents significant technical challenges, including vast distances, propulsion systems capable of reaching relativistic speeds, life support systems for long-duration missions, and protection against cosmic radiation. Concepts like solar sails, ion propulsion, and advanced nuclear propulsion are being explored for potential interstellar missions in the future. 110. The Local Group is a small cluster of galaxies that includes the Milky Way, Andromeda M31, and about 54 other smaller galaxies. It spans about 10 million light-years across and is gravitationally bound. The Local Group provides insights into galaxy formation, dynamics, and interactions. The Milky Way and Andromeda are on a collision course, expected to merge in about 4 to 5 billion years, creating a new galaxy dubbed Milkomeda. 111. White dwarfs are the remnants of stars like the Sun after they have exhausted their nuclear fuel and shed their outer layers. They are extremely dense objects, typically about the size of Earth but with masses comparable to the Sun. White dwarfs cool down over billions of years, eventually becoming faint black dwarfs. They're crucial for understanding stellar evolution and are used as cosmic clocks to estimate the ages of star clusters and the universe. 112. The zodiacal light is a faint, diffuse glow extending along the ecliptic plane of the sky, caused by sunlight scattered by interplanetary dust particles. It is visible from Earth after sunset or before sunrise as a cone-shaped glow in the western or eastern sky, respectively. The zodiacal light is a prominent feature in the night sky and serves as a reminder of the vastness of our solar system and the presence of interplanetary material throughout it. 117. Planetary rings are thin, disc-shaped structures composed of particles ranging from micrometers to several meters in size, orbiting around planets. Saturn is famous for its extensive ring system, which consists of countless small particles of water ice and dust. These rings are believed to be remnants of moons or asteroids that were torn apart by tidal forces or impacts. Studying planetary rings provides insights into the dynamics of celestial bodies and the formation of planetary systems. 118. Tidally locked planets are celestial bodies where one side permanently faces their parent star, while the other side remains in perpetual darkness. This phenomenon occurs due to the gravitational interaction between the planet and its star, causing the rotation period to synchronize with the orbital period. Examples include Mercury, which is tidally locked to the Sun, and many exoplanets discovered around other stars. Tidally locked planets have extreme temperature differences between their day and night sides, posing challenges for potential habitability. 119. Planetary migration is a concept in planetary science where planets change their orbits over time due to gravitational interactions with other planets, debris disks, or their host stars. This process is believed to have played a crucial role in shaping the architecture of our solar system and other planetary systems. For example, Jupiter's migration may have influenced the formation and positions of other planets in our solar system, impacting their orbits and stability. 120. Rogue planets, also known as interstellar planets, are planetary mass objects that do not orbit any star. These free-floating planets can be ejected from their parent star systems due to gravitational interactions or disruptive events such as supernovae. Rogue planets drift through interstellar space, possibly harboring moons and atmospheres despite lacking a host star's warmth. Detecting and studying rogue planets provide insights into planetary formation processes and the prevalence of free-floating worlds in our galaxy. 121. Astrochemistry is the study of the chemical elements and compounds found in outer space, including molecules, ions, and atoms. It explores the formation and interaction of these substances in environments such as interstellar clouds, protoplanetary disks, and the atmospheres of planets and moons. Understanding astrochemistry helps scientists unravel the chemical evolution of the universe and the origins of complex molecules essential for life. 122. The Kuiper Belt is a region of the solar system beyond Neptune's orbit, extending from about 30 to 50 astronomical unit from the Sun. It contains numerous small icy bodies, dwarf planets like Pluto, and other trans-Neptunian objects. The Kuiper Belt is believed to be a relic of the early solar system's formation and provides insights into the dynamics of planetary migration and the origin of short-period comets. 123. Planetesimals are small, solid objects believed to be building blocks of planets. They form in protoplanetary disks around young stars through collisions and accretion of dust and ice. Planetesimals range in size from meters to hundreds of kilometers and can merge to form larger bodies such as asteroids, comets, and eventually planets. Studying planetesimals helps scientists understand the early stages of planetary formation and the evolution of planetary systems. 124. Astrobiology is the interdisciplinary study of the origin, evolution, distribution, and future of life in the universe. It combines elements of biology, astronomy, chemistry, geology, and physics to investigate the conditions and processes that may support life beyond Earth. Astrobiologists explore extreme environments on Earth and search for habitable conditions on other planets, moons, and celestial bodies. The search for extraterrestrial life is a central focus of astrobiology, with missions to Mars and ocean worlds like Europa and Enceladus aiming to find evidence of past or present life. 125. The Great Red Spot is a massive, persistent anticyclonic storm on Jupiter, larger than Earth in diameter. It has been observed for centuries and is characterized by its swirling clouds of reddish hues. The storm's longevity and dynamics provide insights into Jupiter's atmospheric processes and the behavior of large-scale storms in planetary atmospheres. Studying the Great Red Spot helps scientists understand the complexities of gas giant planets and their atmospheric dynamics. 126. Multiverse theory posits that our universe, with its specific set of physical laws and constants, may be just one among many universes existing simultaneously within a larger cosmic framework. This concept arises from several theoretical frameworks in physics and cosmology, such as string theory, quantum mechanics, and inflationary cosmology. These theories suggest that during the early stages of the universe's formation, different regions could undergo separate phases of inflation, leading to the formation of distinct bubble universes. Each bubble universe within the multiverse may have its own unique properties, including variations in fundamental constants, laws of physics, and even the number of dimensions. 127. The idea of a multiverse challenges the traditional notion of a singular, unique universe governed by a single set of physical laws. Instead, it suggests that the universe we observe may be just one among countless others, each potentially following different rules and exhibiting different physical phenomena. For example, in the many worlds interpretation of quantum mechanics, every quantum measurement is thought to split the universe into multiple branches, each representing a different outcome. This interpretation implies that every possible quantum state and event occurs in its own separate universe, collectively forming a vast landscape of parallel realities. 128. String theory, a prominent candidate for a unified theory of physics, also supports the idea of a multiverse. According to string theory, our universe is embedded within a multidimensional space known as the bulk, where different configurations of extra dimensions and fundamental forces could give rise to a multitude of universes with varying properties. These universes, often conceptualized as different points or regions within a larger landscape of possibilities, represent different vacuum states or solutions to the equations of string theory. The vastness of this landscape suggests that our observable universe's specific characteristics, such as particle masses and force strengths, may be just one of many possible outcomes dictated by the underlying physics of string theory. 129. While the concept of a multiverse remains speculative and theoretical, it has profound implications for our understanding of cosmology, fundamental physics, and the nature of reality itself. It challenges scientists to explore new ways of testing and verifying these ideas, often pushing the boundaries of observational and experimental capabilities. For instance, efforts to detect signatures of other universes or parallel realities beyond our own remain a subject of active research and debate within the scientific community. These efforts include studying the cosmic microwave background radiation for anomalies that could indicate collisions between bubble universes or searching for indirect evidence of extra dimensions predicted by string theory. 130. Philosophically, the concept of a multiverse raises fundamental questions about the nature of existence, the role of chance, and the structure of the cosmos. It prompts inquiries into whether our universe's laws and constants are finely tuned for the emergence of life and intelligence, or merely one of countless combinations that could support different forms of existence. The exploration of multiverse theories encourages a broader perspective on the vastness and diversity of possible universes, inviting contemplation of humanity's place within an infinitely complex and interconnected cosmic tapestry. 131. The many worlds interpretation of quantum mechanics proposes that every quantum measurement results in the splitting of the universe into multiple branches, each representing a different outcome. This interpretation implies that all potential quantum states exist simultaneously in their own separate realities, forming an expansive multiverse of parallel universes. Each universe within this framework would unfold according to different sequences of events and quantum probabilities, encompassing a vast array of possible histories and futures. 132. The mathematical multiverse concept extends the idea that mathematical structures and equations can describe different physical realities. According to this perspective, the existence of multiple universes is rooted in the diversity of mathematical possibilities. Each mathematical structure represents a potential universe with its own distinct set of physical laws, constants, and properties. This theory posits that the universe we observe is just one instantiation of mathematical principles that could manifest in infinite variations across different mathematical landscapes. 133. The landscape multiverse theory emerges from string theory, which suggests that our universe is one of many possible configurations within a larger landscape of potential universes. In string theory, the fundamental particles and forces of nature arise from the vibrational patterns of tiny, multidimensional strings. The landscape of string theory encompasses a vast array of possible vacuum states or solutions, each corresponding to a different set of physical constants, dimensions, and particle properties. This theory proposes that the observed properties of our universe, such as the strength of gravity or the masses of elementary particles, are a result of the particular vacuum state we inhabit within this landscape. 134. The cosmic bubble multiverse hypothesis suggests that new universes could continuously form within an expanding multiverse. According to inflationary cosmology, during the early stages of the universe's expansion, different regions could undergo rapid inflation, creating bubble universes separated by vast expanses of space. Each bubble universe would have its own unique set of physical laws, constants, and initial conditions, potentially giving rise to diverse environments and phenomena. These bubble universes would exist within a larger cosmic framework, interacting with each other through gravitational effects or other cosmological forces. 135. Brain multiverse theory proposes that our universe exists on a three-dimensional membrane brain within a higher dimensional space known as the bulk. This theory suggests that multiple brains, each representing a distinct universe with its own set of physical laws and constants, could exist parallel to our own within the larger dimensional framework. Interactions between these brains could potentially influence cosmic phenomena observed in our universe, such as the distribution of dark matter or the behavior of gravitational waves. 136. Parallel universes in fiction have been a recurring theme in science fiction literature, films, and television. These narratives explore hypothetical scenarios where alternate realities exist, diverging from our own due to different historical events or decisions made by characters. The concept of parallel universes in fiction serves as a thought-provoking exploration of the consequences of alternate choices and the nature of reality across different dimensions. 137. Quantum decoherence and parallel realities. Quantum decoherence is the process through which quantum systems lose their coherence and become entangled with their environment, leading to the emergence of classical behavior. Some interpretations of quantum mechanics suggest that quantum decoherence could contribute to the formation of parallel realities or alternate universes. These interpretations propose that every quantum measurement results in the splitting of the universe into multiple branches, each corresponding to a different outcome of the measurement, forming a vast multiverse of parallel realities. 138. Anthropic principle and multiverses. The anthropic principle suggests that the observable universe must be compatible with the existence of observers, such as humans, because without observers, the very question of why the universe is the way it is would not arise. In the context of multiverses, the anthropic principle is often invoked to explain why our universe appears finely tuned for the emergence of life and intelligent beings, despite the vastness and apparent randomness of the cosmos. It posits that the physical laws and constants of our universe may be just one of many possible configurations across different parallel realities where conditions suitable for life vary widely. 139. Eternal inflation theory. Eternal inflation theory proposes that our universe is part of a larger multiverse where inflation, a rapid expansion of spacetime, continues indefinitely. According to this theory, different regions within the multiverse undergo varying rates of inflation, leading to the formation of bubble universes separated by inflating regions. Each bubble universe could have its own distinct properties, such as different physical constants or laws of physics, shaped by the initial conditions and dynamics of inflation. 140. Philosophical implications. The concept of multiverses raises profound philosophical questions about the nature of reality, existence, and the role of observation. It challenges traditional views of a single, unique universe by suggesting that our reality may be just one of many possible configurations. Philosophers explore the implications of multiverse theories on concepts such as free will, determinism, and the nature of truth, offering new perspectives on the limits of human knowledge and understanding. 141. Observable effects. While direct observation of other universes within the multiverse remains beyond current technological capabilities, some theories propose indirect ways to detect or infer their existence. For example, anomalies in the cosmic microwave background radiation or patterns in the distribution of galaxies could potentially provide clues about interactions between our universe and neighboring universes within the multiverse. Scientists continue to develop theoretical models and observational techniques to explore these possibilities and test predictions arising from multiverse theories. 142. Holographic multiverse theory suggests that a three-dimensional universe might be a projection from a two-dimensional surface located at the cosmological horizon. This theory derives from principles of quantum gravity and string theory, proposing that information about our universe's structure and dynamics is encoded on the boundary of the observable universe. Different projections or holograms could correspond to distinct universes with varying physical laws and properties. 143. Cosmological natural selection hypothesizes that universes capable of producing black holes might be favored within a multiverse scenario. According to this theory, the formation and evolution of black holes in parent universes could give rise to offspring universes with similar physical constants and laws conducive to black hole formation. Over time, this process could influence the distribution of universes within the multiverse, potentially leading to the emergence of specific physical characteristics observed in our universe. 144. Quantum foam refers to the fluctuating structure of spacetime at extremely small scales, where quantum uncertainties lead to the formation of virtual particle pairs and fluctuations. Some multiverse theories suggest that interactions within this quantum foam could connect different universes or allow for information exchange between them. These interactions might manifest as subtle effects or signatures observable within our universe, providing potential clues about the existence of neighboring universes within the multiverse. 145. Anthropic multiverse theory proposes that the observed properties of our universe are influenced by the necessity for life to exist and observe it. This theory posits that the laws and constants of our universe are finely tuned to permit the emergence of intelligent life forms capable of observing and contemplating the universe's structure. Within the multiverse context, the anthropic principle suggests that our universe's parameters are just one of many possible configurations that could support life, reflecting the diversity of potential universes across the multiverse landscape. 146. Membrane multiverse theory proposes that our universe exists on a three-dimensional membrane within a higher-dimensional space known as the bulk. Within this framework, multiple membranes or branes could coexist, each representing a separate universe with its own distinct set of physical laws and constants. Interactions between these branes within the bulk could potentially influence cosmic phenomena observed in our universe, such as gravitational forces or the distribution of matter. 147. Chaotic inflation theory suggests that during the early stages of the universe's expansion, different regions underwent rapid and irregular inflationary periods. This theory proposes that these inflationary episodes created pocket universes within a larger multiverse, each with its own unique initial conditions and physical properties. The diversity of cosmic structures observed across the multiverse could be attributed to these variations in initial inflationary dynamics. 148. Timeless multiverse hypothesis posits that time may not flow uniformly across all universes within the multiverse. According to this hypothesis, each universe could experience its own arrow of time, directionality of causality, or even exist in a state without time altogether. This concept challenges conventional notions of temporal dynamics and suggests a diverse range of temporal experiences across different realities. 149. Quantum entanglement and multiverse connections. Some theories speculate that quantum entanglement, where particles become correlated regardless of distance, could facilitate connections between different universes within the multiverse. These entangled states across universes might explain mysterious phenomena or correlations observed in our universe, offering insights into the interconnected nature of reality across multiple dimensions. 150. String landscape and multiverse diversity. String theory's landscape hypothesis proposes that our observable universe is just one of many possible configurations within a vast landscape of potential universes. Each universe within this landscape could arise from different configurations of extra dimensions, fundamental forces, and string vibrations. This theory suggests that variations in physical constants, particle properties, and the geometry of spacetime could give rise to a diverse array of universes across the multiverse. Picture yourself drifting through the serene expanse of the universe, where galaxies swirl in mesmerizing dances and the fabric of reality weaves intricate tales of multiverses. As you gaze upon the cosmic tapestry, each thread represents a different universe, each with its own laws of physics, dimensions, and possibilities. The concept of multiverses offers a profound meditation on the nature of existence, inviting us to ponder the vastness of potential beyond our own reality. In this journey through the cosmos, the idea of multiverses serves as a comforting reassurance that amidst the uncertainties of life, there exists a universe where every dream, hope, and aspiration takes form. It encourages us to embrace the diversity of existence and cherish the beauty of cosmic exploration. Just as stars illuminate the night sky, the multiverse illuminates our imagination with endless realms of possibility. As you prepare to rest, let the thought of multiverses gently guide you into a state of tranquility. Allow the wonders of the cosmos to soothe your mind, easing the weight of everyday concerns. In the quiet moments before sleep, envision yourself floating among the stars, surrounded by the infinite expanse of multiverses unfolding beyond comprehension. May this cosmic journey inspire peaceful dreams and awaken a sense of wonder that lingers softly until the dawn breaks anew. Picture yourself drifting through the serene expanse of the universe, where galaxies swirl in mesmerizing dances and the fabric of reality weaves intricate tales of multiverses. As you gaze upon the cosmic tapestry, each thread represents a different universe, each with its own laws of physics, dimensions, and possibilities. The concept of multiverses offers a profound meditation on the nature of existence, inviting us to ponder the vastness of potential beyond our own reality. In this journey through the cosmos, the idea of multiverses serves as a comforting reassurance that amidst the uncertainties of life, there exists a universe where every dream, hope, and aspiration takes form. It encourages us to embrace the diversity of existence and cherish the beauty of cosmic exploration. Just as stars illuminate the night sky, the multiverse illuminates our imagination with endless realms of possibility. As you prepare to rest, let the thought of multiverses gently guide you into a state of tranquility. Allow the wonders of the cosmos to soothe your mind, easing the weight of everyday concerns. In the quiet moments before sleep, envision yourself floating among the stars, surrounded by the infinite expanse of multiverses unfolding beyond comprehension. May this cosmic journey inspire peaceful dreams and awaken a sense of wonder that lingers softly until the dawn breaks anew.